In modern educational technology, user progression is never a straight line from Lesson A to Lesson B. The curriculum is calculated in real time, responding dynamically to user input. To generate these pathways, the system evaluates the student's current capability and immediately reassembles the sequence of tasks. But before the algorithm can recommend the optimal next step, it has to accurately measure mastery. You can measure a student's height or weight with physical tools. You cannot put a cognitive trait on a scale. Because learning is an invisible construct, engineers rely on psychometrics. They use statistical modeling to reverse engineer a student's actual ability from their chaotic digital footprint. In psychometrics, the trait we want to measure, like mathematical literacy, is called a construct. We have to clearly define that construct before we can look for evidence of it. Historically, international baseline standards measured these constructs through massive testing initiatives. Students sat down, filled out physical booklets, and generated a fixed episodic snapshot of their ability. A digital learning platform operates on a completely different scale. Users engage in continuous, high-volume sessions where every single interaction is captured. This removes the barrier between learning and testing. The entire digital environment functions as a continuous measurement engine. The foundation of this measurement engine is the behavioral log. Tracking whether an answer is simply correct or incorrect does not provide enough data to accurately model human cognition. If we look at a standard behavioral log, we see a structured database table capturing user ID, action type, parameters, and a timestamp. This structure allows the system to capture passive behaviors, recording the milliseconds a user pauses on the interface or time elapsed before their first click. Translating these variables into a reliable measurement requires operationalization. Psychometricians write mathematical rules to determine exactly what combination of time and action constitutes valid evidence of mastery. Executing these rules across millions of students, each generating thousands of log entries, creates an extreme computational load. Without operationalization, raw behavioral data is entirely useless noise. The statistical rules give the data its meaning. Even with defined rules, behavioral evidence requires a rigid structural framework to provide context. This is the skill graph. It serves as an ontological map of all knowledge contained within the platform. The graph charts directional dependencies, defining exactly which foundational nodes, like addition, must be mastered before a student can advance to a more complex node, like multiplication. Individual assignments and content cards are systematically tagged to these specific nodes. There is a strict technical constraint here. Tagging a single task with too many skills creates exponential statistical noise, making it impossible for the algorithm to determine which specific skill the student utilized. By enforcing a precise ontology, the system mathematically isolates what a student actually knows from what they are merely guessing. Maintaining the integrity of the system requires automated quality control. Engineers use a methodology called classical test theory to evaluate thousands of tasks simultaneously. This diagnostic dashboard maps task performance using two primary metrics: item difficulty and item discrimination. By plotting these variables together, the system establishes a clean trend line that represents expected user behavior. When the data contradicts this expectation, the system flags a statistical anomaly. Here, the metrics indicate that weak students are consistently outperforming strong students on a specific task. This anomaly signals a real-world operational failure. The task might have a flawed answer key, a confusing user interface, or a broken question prompt. Classical test theory allows the platform to self-diagnose and purge this toxic content before it corrupts the broader learning data. These architectural decisions dictate how platforms operate in real-world corporate environments, directing millions of user sessions a day. When a student submits an answer, the system cross-references their behavioral log with the skill graph to trigger an automated routing decision. This UI flowchart demonstrates how a single user profile is sorted into three divergent tracks: enrichment, review, or remediation. If a student falls into the remediation track, the algorithm has detected missing prerequisite skills. They cannot progress until these specific foundational nodes are repaired. The algorithm also accounts for memory decay. If a user is absent from the platform for 2 weeks, the system recalculates their mastery levels to factor in natural forgetting. Because the platform only has a limited number of interactions to work with, it calculates confidence intervals to verify that the mastery score is statistically reliable. The adaptive engine is not an automated teacher. It is a probability machine, constantly calculating the optimal level of difficulty required to maintain user engagement. There is a persistent assumption in EdTech that product analytics and learning analytics serve different goals. In reality, pedagogy and profit are mathematically linked. This diagram illustrates the hierarchy of platform metrics. The base layer is built entirely on behavioral logs and item difficulty. The precise tuning of that microscopic data dictates the health of the middle tier, the product metrics. This is where user retention and overall engagement are measured. Those product metrics feed directly into the macroscopic financial outcomes at the apex, specifically gross merchandise value and the lifetime value of the customer. Serving tasks at the optimal difficulty level directly modulates user frustration and boredom. Those two emotions are the primary drivers of platform churn. If the psychometric model controls user frustration, it guarantees retention. User retention mathematically dictates how much revenue a single customer will generate over their lifespan on the platform. Treating psychometrics as a purely academic exercise is a structural error for any platform builder. The measurement of learning and the routing of content function together as the interlocking mechanism driving the entire product. Psychometricians engineer the invisible core loop that sustains the platform's financial viability. Pedagogical quality is the ultimate business strategy.